function, and it is put it here. Yeah. Okay. So in the next step, we have to consider situation. What will be V0 for infinitive of time for steady state? Okay. All right. So when capacitor will be will collect the maximum charge, we know that for that situation, the capacitor, it is like the open circuit. That's right, for steady state. So if the VT is equal 9 volts, and then we consider it like the 9 volts, it is going to infinitive at this moment. So we've got the voltage which has 9 volts. We've got the 6 kilo. The capacitor, it is like the open circuit because the it is full at this moment. So we have to find what is the maximum value in this case for the V0. So as you see, we've got here the voltage divider, as you see. That's right. So the V0 for infinitive of time, where we've got the 9 volts of the voltage for the voltage source, the V0, it is equal, how many? It is the voltage across the 8 kilo ohms at this moment. We've got the 3 resistors, so according to the voltage divider, we've got 9 volts multiplied by in nominator, we have to put the resistances where we observe the V0. So it is 8 kilo over the sum of the resistances in our voltage divider circuit. So it is 6K plus 4K plus 8K. So it is 9 multiplied by 8 kilo over 18 kilos. As you see, kilos will be reduced. So how many we've got here? This can be reduced by 9. So we've got a 1, 2. So it is 4 volts. So this is the final voltage for the steady state. All right. So now we have to find what is the time constants value, tau. As you see, we've got here the RC circuit. So we've got the capacitor. So for capacitors, we've got the tau, which is equal RC. Yeah, that's in general. However, we have to calculating what is this resistances in our case. Okay, how many it is? This resistances is considered from the capacitor point of view. Yeah? In general, we've got the situation we have when we've got the one resistor, we've got the capacitor, and this capacitor is charging through these resistances, and then the tau, it is equal RC. Okay, so how many is this equivalent resistances for our electronic circuits, which is observed by the capacitor? So we have to find what is the RTH or equivalent resistances from these 2 points. Okay. So if we wanted to calculate it, we know what we have to do. using the Thevenin methods, for example. We've got the voltage source here, which has to be changed by short circuit, because we have to have the 0 volts here. So we've got the oh, something was stopped. All right. Yeah. Okay. So here we've got the short circuit by the voltage source. We've got our terminals A and B and 2 resistances. So we've got a 6K, 4K, 8K. So what is the resistances here? As you see, it is the parallel connection of the 6K with these 2 resistances, which are connected in series. So it looks like that. So it is the 6K parallel with the 12K in this case. So how many it is? 6K times 12K K over the 6K plus 12K, and it is equal, it is 16, okay, this is the 4K, 4 kilo ohms. This is the equivalent resistances which is observed by the capacitor, and this resistances let us to find the tau. How many it is? The tau will be equal RTH multiplied by C. So it is 4K times, what is the capacitance of the capacitor? It is 100 microfarads. Okay, we've got it. So this is the 4 times 10 to power 3 times 100 micro, it is 10 to minus 6. So it is the 400 times 10 to minus 3. Okay, so 1, 2, 3. Okay, so this is the 0.4 seconds. So that's the tau value. Great. So let's take another piece of paper. Okay. So now we can express this function.
I'm sorry.
Yeah.
So this capacitor is charging through, like it's charging through 4K resistor, right?
It's charging through
4K.
Yeah. This is this circuit. It is like the equivalent to this one.
Yeah, but it shouldn't be it higher, because the resistors on the right will be stealing current from
No.
will be discharging this capacitor.
No. Look, in typically, if we've got such the circuits, yes, as you see, we've got the one resistor and the another ones. So as you see, this current which is which is not passing through, but which would be appear during the charging process in this branch where we have the capacitor, it depends on these resistances. As you see, we've got the junction here. So in fact, this resistor will be limited this current. However, this current will be divided also by, it will be divided or split out in this junction, depending on the value of the resistances in our electronic circuits. So
capacitor should charge slower with this resist. resistors on the right.
Yeah, that's right. So that's why we have to finding what is the equivalent resistances from the capacitor point of view. So that's why we can reduce this example, this the circuit, by the equivalent one, like that one. So in this case, our 4K, 4 kilo ohms, it is the RTH. It is the same circuit, in fact. Okay.
Can I?
So now it's clear?
I'll try. I will try to. Mm, can I try to screen share something?
Yeah.
But you have to close your screen sharing.
I have to stop sharing, yeah?
Yes. I wonder if
Okay.
this will work.
Great.
Okay. This. Can you see this?
Yeah.
Yeah. So here is a higher voltage than here after 300 milliseconds.
Yes.
Shouldn't be this same voltage as this?
No. It not will be the same voltage. It's correct.
Okay.
This is correct because I don't. You don't see my mouse, the indicator. Okay. It is not the same because you've got the parallel. You've got the parallel connections of some resistances to your capacitor. So that resistances will be decreasing this potential before the first resistor. So it is correct what you saw. What you saw, this is correct.
I stop sharing so you can.
Okay, thank you. Okay, we've got it? Yeah. Okay. Great. So now we can find the expression for the V0, because we've got the maximum value. The maximum, it is 4 volts. The tau, it is calculated. So in general, it will be the Emax value times 1 minus e power to minus t over tau, yeah? So in our case, it is Emax, it is the maximum value. So this is the 4 volts times 1 minus e to minus t over 0.4 seconds. That's the expression when the voltage, when the input voltage is rapidly going up to 9 volts. And the V0 will be looks like that. And now is according to this function, we'll observe that the V0 is going up and wanted to go to the in this case it is 9 volts for the VV voltage, input voltage. Here for the blue curve, the maximum it is 4 volts. Okay, all right. However, we know that the pulse is ending here after 0.3 seconds. so the charging process will be going up to this moment, yeah, because the input voltage is decreasing, rapidly decreasing to 0. So for the time equal 0.3 seconds, something is changed. What happened? The charging process is stopped. The capacitor is not full, of course, and after this time, 0.3 seconds, we can observe the discharging process. Okay, so how looks like the discharging process? We know it. It is given by that function. And this function is represented like the Emax e power to minus t over tau, where Emax, it is this point. This is Emax. What will be the Emax value for discharging process in our case? It will be this point. That's right, because here we observe the discharging function. Okay, so now in the next step, we have to find what is the point here, what is the voltage, V0 voltage, after 0.3 seconds. Yeah, okay. So let's do it. Another thing. All right. This function is given when the discharging process is starting for the time equals 0. Yeah? What happened, or how we can describe this function when this discharging process is shifted by some value, for example, 0.3 seconds, and we observe the discharging process from this point. So this function, it is in fact the same like this one. However, the time is shifted. Time is shifted by 0.3 seconds to the right. So what we have to do, the time should be, for the value of time, should be subtract the 0.3 seconds over the tau. Yeah. If we shift the function to the right, we have to subtract the shifted the shifting value. If we shift it to the left, we have to add the shifted value to the time. Okay, so you have to remember it, because we've got this situation that this discharging process is starting from for not the time equal 0 seconds, but 0.3 seconds. So as you see, we have to shift this function also. Okay, so we have to find this Emax value for the discharging process. So it is very simple to find, because we've got the expression for V0, yeah, for the charging process, and we have to find just the V0 for 0.3 seconds from this example, from this the function. So it is given like that: 1 minus e to minus 0.3 seconds. I have to just substitute by time the value of 0.3 seconds over 0.4, that is the tau constants. And how many it is? I found it, and it is equal to 2.11 volts. Okay, so we know that this point, it is 2.11 volts. So this is our initial value for discharging process function. Okay, so the next step, we have to find the V0 for the time higher than 0.3 seconds. Great. So this function is given by that formula. That's the typical. However, in our case, it will be the E max. It is the initial value. It is 2.11 volts times E powered to minus t. However, as you see, this function, our function, should be shifted by 0.3 seconds. Okay, so it is E powered to minus t minus 0.3, okay, over the tau constants, 0.4. Okay, that's all. So this is the expression for V0 after 0.3 seconds of time. Great. How we can describe it using the mathematical form? The V0 can be described in that form. It is 0 for the time lower than 0 seconds. It is 4 times 1 minus 8 minus t over 0.4 seconds, 0.44 seconds, okay, for the t between 0 and 0.3 seconds. Yeah. And it is 2.11 e powered to minus t minus 0.3 over the tau 0.4, yeah, for the time higher than 0.3 seconds. So this is the one form of representation of our final V0 function, which looks like that. Okay, which looks like that. Okay, how we can express the function in another way? Tell me, do you hear something about the unity function? Do you hear something about the unity function?
No.
Okay.
No, to be honest, no.
Okay, so what is the unity function? The unity, oh, all right. So unity function, as the name says, it is the function which has the maximum value equal 1. Yeah, it's the unity function. It looks like that. Here we've got the 1. This is the 0 seconds. And this is the function like ut. This is unity function. Okay. What will happen when we will shift the unity function by some value of time, for example, by 0.3 seconds? As I said previously, the unity function for that case, it is given by the formula of ut minus 0.3. Yeah, that's right. Okay, so please tell me, how will be look like the unity function, which will be built like the subtraction of ut minus 0.3. If I will subtract these two functions, what I will get? 0 minus 0, it is 0. Okay. 1 minus 0, it is 1. 1 minus 1 gave us the 0. So what, as you see, I've got some window which is given by the formula like ut minus 0.3. Yeah. So sometimes the unity function, it is called like the gate function. Yeah. Why? Because if you wanted to, for example, show only the, or find the expression for some periodical function, but we have to, for example, starting from 0 seconds, we have to use the unity function or gate function. And for example, sine expression. Okay, maybe another way. I've got this sine function. It just looks like that. Yeah. Okay, as you know, the sine function hasn't the beginning and the end and ending. So I wanted to get that function. Yeah, this is the sine function. However, from this point, from the 0 seconds, it is 0. Before the 0 seconds is 0, and only from this point is starting the sine function is appeared. So what I have to do? The sine function should be multiplied by unity function. So this function is expressed by this one. So as you see, I use the unity function or gate function to wyzerować. Do you know how it is in wyzerować? Po angielsku?
Cancel out.
Maybe we have to get the 0 before the 0 seconds, yeah, point. So this function is reduced to 0, yeah, by unity function. We have to multiply it by such function. Yeah. Okay. So the same story it is in our case. As you see, I can build the unity function which is starting from the 0 to some point in the time domain. So as you see, I can use this function or unity function in our case. Okay, let's take a look how we can express the V0 function by using the gate functions. Okay, so we know that between the 0 to 0.3 seconds, we've got that function. However, we wanted to get only in this range of the time. So we can take this function, yeah, and let's multiply it by our what? Gate function, which is given by such formula, by this window. Okay. Okay. So as you see, everything what is here, in fact, it is the function like that. For example. Yeah. And then we've got the 0. Okay. So this is the blue function. Okay. What happened after 0.3 seconds? We've got that formula. Okay, so we have to add to the blue curve the next function. Okay, however, we have to multiply it. This formula should be multiplied by unity function. Yeah, which one? U t minus 0.3. Yeah? By this one. Yeah? This function should be equal 0 before 0.3 seconds. Yeah, so we've got the unity function is equal 0, and this equal 1 after 0.3 seconds. So using this unity function like u t minus 0.3, we've got the rest of the function. So as you see, this is two types of how we can express two types to express express the v0 function using the gate function or that typical mathematical expression for presented, which is presented here. Great. Okay, that looks like the first example. Okay, and I think we can go to the next one. What do you think? Can we?
Yeah, we can.
Yes?
Yes.
Great. Okay. All right, so the next example. In the next example, we have to find the initial current which is passing through by the coil. This is one thing. Also, the initial value of it. It is the E in. Yeah. In the next step, we have to find the mathematical expression for the current IL, current which is passing through by the coil, when the switch S2 is closing and S1 is opening. Okay, and what you have to do in the last case, we have to just draw the waveform for the current which is passing through by the coil. All right, so what we have to do firstly, we have to get the initial value of the current in. Why? Because maybe you remember from the lecture, the current IL can be expressed by the general expression. In fact, general function. It is given like that. IF, it is the final value of the current plus the initial value minus final E powered to minus T over tau. All right, so we have to find the EN and EF. Okay, firstly, in the first step, we've got the situation where when the S1 is closed, S2 is open. So here we've got the open circuit, so it doesn't matter what happened here. At the first moment, we've got the situation when S1 is closed, so we've got just the R3 resistances, we've got the battery here, and we've got the coil. Yes. However, as you see, it is the steady state. Yeah, it is the steady state. So the coil, in fact, for the steady state, it is like the. Do you remember? What is the resistance?
It's shorted.
Yeah, it is like the short circuit, of course, Igor. That's right. So we've got, in fact, the coil. However, its resistance is equal to 0. Yeah, for the ideal situation. So we've got the short circuit here. All right. So what is the initial value of the current for our coil? It is the simple circuit, one battery and one resistor. What is the current here? It is the E over R3. What is the direction of the initial current according to IL? It is positive potentials here, so the initial current, it is given such way. So it is opposite to the IL. So that's why for initial current, we have to put the minus here. All right, so it is 6 volts over 1K. It is equal minus 6 milliamps. Okay, that's the initial current. All right, next step. What happened when the S1 is opening and S2 is closing? We've got situation like that. We've got the coil. R2 is here, S2 is shorted. This is R1, and here we've got the current source with 12 milliamps. Great. Oh, so what we have to do in the next step, we have to find the final value of the current which will be passing through by the coil. In this case, look, the current is given by that direction, so there's no any way, but there's no any way this is very simple to find what is the real direction of the current here in this in the branches. Yeah, because this input current should be split out to the dot currents. For example, this is the I1 and I2, doesn't matter. However, this current will be passing through by the coil in this direction, and it is the same like the current IL, which is given here. So as you see, for the final current, we'll have the same sign. Okay, all right. So what will be the final current passing through by the coil? So we have to determine it for the steady state. That's right. So for the first case, we have to find what will be the RTH from the coil point of view, and what will be the ETH, which is across the coil. Why we have to find them? Because we wanted to get the final current passing through by the coil. So it is given by such formula in general, yeah, using the Thevenin methods. That's right. So previously we have to find the RTH. Okay. Great. So first of all, if we wanted to find the RTH, we have to remove the coil, and we have to take it off all the sources. As you see, we've got the current source here. the current source, it is replaced by the open circuit because we wanted to reduce the current to 0 value. So in fact, finding the RTH, we've got just the R2 and R1. That's all. Here we've got the open loop here. Yeah, great. So the RTH, it is just the R1 plus R2, and in our case, it is how many? 8.2K plus 2.2K, so it is 10.4 kilo ohms. It is the RTH. What will be the ETH? Look, the ETH we have to find also when the A and B points or terminals are open. So we still haven't any coil here. So we've got the situation like that. However, we're coming back with our sources. Yeah. So we're coming back with the current source. Okay. Great. So ETH it is here. Okay. However, as you see, R2, the resistor R2 is in open loop here. The A and B points are open. So ATH, in fact, this is the voltage across the R1, yeah, because we haven't any voltage drop on the R2 because here the current is equal 0. Yeah, that's right. So how we can find the current through? So how we can find the ETH on the R1? In fact, this is the current source which is given, which is produced the 12 milliamps, which is passing through by the R1. So as you see, it is very simple to calculating the ETH. So it is just the current multiplied by R1. So it is 12 milliamps times 2.2K. So it is equal 26.4 volts. Yeah. Okay, this is kilo milli, so it is reduced. Okay, so we've got the ETH. Great. So, in fact, we've got the voltage source. Oh, sorry, we've got the voltage source ETH with the RTH value, and now we're coming back with the coil. Yeah, EF. However, we know what is the resistances for the steady state for the coil. It is equal to 0. Yeah, that's right. So the EF, in fact, it is equal how many? ETH over RTH. That's all. So it is the 26.4 volts over the 10.4K or kilo ohms. Yeah. So it is equal 2.54 milliamps. So that's the final current. Yeah. Great. Next thing. We also remember about the time constants because it is used in the in the expressions. So as you see, what the question is, what will be the tau value? This is not the RC but RL circuit. So please remember that the tau in such circuits, the tau, it is given by the L over RTH or R formula. In our case, it is the RTH. That's right. This is the resistances which is observed by the coil. Yeah? And this is the same story. We've got the coil, and here it is like it is the equivalent, the resistances. All right. So let's calculating. right? So the tau will be equal. L, it is 680 millihenries over the RTH. RTH, it is 10.4 K. How many it is? It is around 65.4 microseconds. This is our tau value. Okay. Great. So now let's subtract. Let's finding the IL value. Coming back to our expression, general expression for it. All right. So it is again the final value plus initial minus final e power to minus t over tau. So it is equal. At the final, it is 2.54 milliamps plus the initial was minus 6 milliamps. Initial was minus 6 milliamps.
Whoa.
Minus the final, it is the 2.54 milliamps times e power to minus t over tau. Tau, it is 65.4 micro. Okay, so in fact, this is the 2.54 milliamps minus 8.54 milliamps power to e multiplied by e to minus t over 65.4 micro. Okay, so
Well, it should be 2.64.
Where?
From current, final current. Above. Oh, well.
Final current?
Yeah, final current should be 2.64. Yeah.
60? Okay, so I'm just...
I got 54.
Not the... Okay, I'll check it.
It's good.
Calc. All right, so it is the...
Oh, no, it's okay. Okay.
Yeah.
Everything's fine.
No, it's correct.
Yeah, it's fine. Sorry.
No, don't worry. Okay. So let's plot this formula. So the initial value was minus 6 milliamps when the S1 was closed and S2 was open. So this is the current IL. Okay, we've got the minus 6 milliamps, and it is minus 6. And suddenly, when we change the switches, we will observe what the current is going to the final value equal 2.54 milliamps. Okay. Okay, and according to such formula, okay, so it looks like that. Exponential function, all right, and somewhere it is tau value, and after 2 tau, and so on, 3, 4, 5, and for example, this is the 5 tau. So we can say that after 5 tau, so 5 times 65.4 microseconds, we can we can say that we've got the steady state. Yeah? That's right. That's right. So that looks like the changing of the current, which is passing through by the coil in our example. As you see, it is a very good idea to remember, in fact, the general expression for the current or voltages for the coils. Why? Because if we'll have the initial value not equal -6 milliamps, but zero milliamps. So everything, as you see, everything is reduced, in fact, here. So it is so easy, everything to calculating it. Great. What else? I think it's enough about this example. Now we can go to the next one when we'll have not the DC but AC analysis, in fact. Okay. So can we start with the next example? Third one?
Yes.
Okay. Great. Please tell me true. This type of examples is known by you or not?
Not really.
Not really. Okay. Because sometimes the people from the some people have had some such examples on the middle school, I think. However, maybe it is not true. I don't know. Okay, so we are going to the AC analysis. So you have to remember that, in fact, the Ohm law is working also for AC analysis. Any theorems also still working for AC. Where's the changes? Where we have the changes? We're not operating on the resistances, but we're operating on the impedances. Okay, so the impedance is consists by two parts: the real and imaginary part. The real one, it is the resistances. The imaginary part, it is the reactances. So if we wanted to talking about the imaginary part, we have to use the indicator, which tell us that we are talking about the imaginary part. So it is the J. Okay. So between them, it is plus or minus. It depends what character has the reactances. We know that we've got the coil and the capacitor. From the lecture, you know that we've got the phase shift between the current and the voltage across these components. Yeah. Sometimes the current is leading or leads the voltage, or voltage leads the current by 90 degrees. Yeah. And it depends on what type of components we've got: coil or capacitor. How it looks like in how it looks like the reactances, how it looks like the impedance of the pure resistance. So the pure resistor, we know that we've got some resistances, and there is no coil, there is no capacitance, and so on. So, as you see, there's no reactances here. That's why the pure resistor has the impedances equal its resistances. That's all. So we can draw it where here we've got the J axis, and this is the real part, and this is the imaginary part, it is the J. So the pure resistor has only the resistances. Right. What about for example, coils, inductors? We know that the pure coil hasn't any resistances. The resistance equals 0. So we put here the 0. Okay, so I don't write it. And it has some reactances. Yeah, inductance has some reactances, inductive reactances, and it is given by the formula like the J, X, L. However, it is positive. It is positive, and we draw it in such way. It is the XL. We've got the 90 degrees here. What about the coil? What about the capacitance? The capacitor? It is the same, but we've got the minus here. So the capacitor on the XC, it is minus 90 degrees here. That looks like the impedances on the according to this. This is the plot of the impedances for any three types of components using the imaginary and real part of the plot. So if you know that at this moment, we can go to the to solving this this example. Okay, so we have to find the voltage across the resistances, coil, capacitance, capacitor, and the V1 using the VDR, yeah, voltage divider rule. Okay, so let's do it. Oh, okay, let's starting with the R. Because we are talking about the sine waveforms here, and this is the AC analysis, on the lecture I told you that we have to indicate the higher and lower potential of the sources, yeah, and we use the positive pulse of the sine waveform to indicate where is the positive and where is the negatives. And why? Because of course the periodically the polarity are changed. Okay, so if we considered only the one pulse, the positive pulse of the sine waveform, we'll have the positive here, minus, plus, minus, plus, minus. So the voltage drops. It is looks like that. Okay, so as you see, we can use the voltage divider very quickly to find the VR. So it is the input voltage multiplied by the impedance which is on the VR value. So it is the ZR over the sum of the total of the rest impedances. So it is the impedance ZR plus ZL plus ZC. Okay. Okay. So maybe at the beginning, let's calculating the impedances and the denominator. What is it? In fact, this is the input or total impedance. In fact, yeah, which is observed by the voltage source. Okay, how many it is? Z total, it is in fact ZR plus ZL plus ZC, and it is equal Okay, let's write the for example this impedances using the rectangular form. It is equal 6 ohms. This is the impedance of the coil, so it is the plus J9 ohms, and this is the capacitor. For the capacitor, we've got the minus J17 ohms. Okay, so as you see, it is given, the total impedance is given by the rectangular, it is given by the value using the rectangular form in such way. This is 6 minus J8. Okay, how we can express it using the polar form. In the polar form, we can draw. We can write the impedance for the pure resistor like this: 6 ohms, yeah, with the angle 0. Okay, plus for the coil, we've got the 9 ohms with angle, as you see, plus 90 degrees. Plus for the capacitor, it is the 17 of the ohms with angle minus 90 degrees. Okay. Okay, so this is the representation of the impedances in the polar form, and this is representation for the rectangular form. Okay, look, I told you on the lecture that it is much more easier to making the multiplication, for example, using the polar form than the rectangular one. So that's why it is, I think it is better to change the rectangular form for the ZT to the polar form. Look, we can adding the values using the polar form in this case, as you see. So we can make it using the rectangular form. Okay, so this is just, I just wanted to show you the representation in the polar form for this ZR and ZL and ZT. Okay, so if I wanted to change the rectangular form for ZT, the polar form, I have to calculating what? The Z value. The Z value, it is given by the real part of the number squared plus imaginary part of the number squared. So it is equal 6 squared plus 8 squared. As you see, every time we've got a plus here, it doesn't matter that we have the minus or plus here, yeah, because we've got the squared here. And please remember, don't put it here, the J. J, it is just an indicator that this number is imaginary. It is imaginary number. Okay, so how many it is? Squared from 100, and it is 10. So this is 10 ohms. What about the angle? What about the angle? The angle, it is equal, how many? Arcus tangent function from imaginary part over the real part of the number. Imaginary, it is minus 8. Real, it is 6. So if you use the calculator where the Arcus tangent is available, you will get the minus 53.13 degrees. Okay, so this number in the polar form it is equal 10 ohms with angle minus 53.13 degrees. How it looks like on the impedance plot. Look. The resistances, it is 6 value. The imaginary part of the number, it is minus J8. So if here it is 6, 7, 8, it is minus, so it's going down. So it is minus 8. So this is the ZT. The length of this vector, oh sorry, the length of this vector, it is 10 ohms. Here, 6, 8, this is 10. And this angle, phi, it is minus 53.13 degrees. Okay. How we can get this this plot? Very simple. Using graphically. Because we've got the resistances here, it is 6. The coil, it is plus 9. So it is 9. The capacitor, it is the reactance is equal to minus 17. So it is going somewhere minus 17. So if we're summing up the imaginary part of our impedance number, we will have the minus 17 plus 9, it gave us minus 8 here. So as you see, that's why we've got this number in such way. Great. So we've got the ZT. We can make it faster on the time it is correct. The speed of the classes is okay at this moment.
It's okay.
Okay. So I told you that VR, it is E multi-time by times the R ZR over the ZT, in fact. So it is equal. Look, here we've got the multiplication, and here we have to divide the numbers. So as you know, now you know it. It is much more easier to make it by using the polar form of the numbers. So let's do it based on the polar form number. Okay, E, it was the 50 volts with angle 30 degrees. Yeah. Okay. Times the pure resistor. The pure resistor, it is just the 6 ohms with angle 0. Over ZT. ZT, it is 10 with angle minus 53.13 degrees. Great. Okay, so how we can make the calculation on using the polar forms? Very simple. The values should be multiplied. So 15 times 6, it is 300. Okay, with angle, if we multiply two numbers in polar form, we have to adding its angle. So 30 plus 0, it is 30 degrees over the 10 with angle minus 53.13. Okay, if we wanted to divide the two numbers, we have to divide it modules. So it is 300 over 10, it is 30. With angles, dividing, we have to subtract the angle. 30 minus 53.13. 53.13 degrees. So it will be equal 30 minus gave us plus, so it is 83.30 degrees. So that's the voltage across the resistor is given by such value. Okay, let's go to calculating the VL. The VL, it is the same, E times ZL over Z total, yeah, according to the voltage divider rule. And again, 50 with angle 30 times ZL. ZL, it is 9 ohms, it is inductor, so it is 9 with angle positive 90 degrees over 10 with angle minus 53.30. So it is equal 450 with angle. Okay, we've got the multiplication, so it is 30 plus 90, it is 120 degrees. So it is equal 45, yeah. And now we have to calculating the angle. 120 minus 53.30, so it is around 173.30 degrees. Okay, great. And VC, very quickly. It is the 17 with angle minus 90 degrees, because this is the capacitor, over the Z total. So it is given 17 850 with angle, as you see, 30 minus 90. So it is the minus 60 over. It is equal 85 volts with angle minus 60 minus, so plus 53.30. So it is the minus 6.87 degrees. Great. What about the V1 value? Look, as you see, the V1, in fact, this is the voltage drop across the VL and VC. Yeah, this is the same. So the V1, it is the sum of the VL and VC. Yeah. Okay. Or we can say that V1, it is the voltage across the sum of the impedances ZL plus ZC. So the V1, it is equal E ZL plus ZC over Z total. Okay. All right. So it is equal E times, okay, ZL plus ZC. Let's come back. ZL plus ZC, it is plus J9 minus J17, it is the minus J8. Minus J8, it is the same like 8 with angle minus 90 degrees. So it is the 8 with angle minus 90 degrees. So it is equal 4 400 over the 10, it is the 40 volts with angle, and with angle, minus 60, minus or plus 53.2. So this is the minus 6.87 degrees again. Okay, so maybe we can draw it in the impedance plot, on the impedance plot. Okay, let's make it. Take the clean one. Okay. Okay. Where's the VR? Where's the VR? Okay. The VR, it is here. It is 30 volts with angle 83.13. Okay. For example, this is the 30 volts with angle, maybe like that, 30. And here we've got this angle 83.30 degrees. Great. That's the R. Okay. What is the VL? VL, it is the 45 volts with angle 173.30. Look, what is the differences between 173.13 and 83.13? If we subtract this and this, we'll get 90 degrees. Do you see it?
Yes.
Yeah. This is the 45 volts. And this angle, it is 173.13. However, between them, we've got the 90 degrees. Okay. Next, DC value. Well, it is 85 volts. Okay, 85 volts with the negative minus 6.87. And this angle here, it is minus 6.87 degrees. As you see, the difference is here also, it is 90 degrees. Okay, great. Okay, let's stop for a while, and let's finding for our electronic circuits here. Let's finding what is the input current here, which is entering to our electronic circuits. This current I. As you see, it is very simple to finding, because if we've got the voltage and we've got the total impedance, which is in fact given by the series connection of the three impedances. So it is in fact our total impedance here. So the current, I, can we finding using just the Ohm law, E over dz total. Yeah. So it is equal 50 with angle 30 over ZT. ZT, it is 10 with angle minus 53.13. So it is equal 5 amperes, yeah, with angle. 30 minus minus, so it is 30 plus 53.30, so it is the 83.30 degrees. Okay, so let's try to mark this current and the voltage on our the impedance plot. The current, it is 5 amperes with the angle 83.30. So as you see, look, it is the same angle like for the voltage drop on the resistor. Okay, where's the input voltage? It is 50 volts here with angle 30 degrees. Okay, so if we find the 30 degrees, it is somewhere here. Okay, and this is E. Look, look what happened if I will finding the equivalent, or if I will sum the imaginary part of the impedance plot or impedance voltage, no, not impedance, but the imaginary part of voltage on the inductor and the coil. If I sum it up, these two vectors, I will get what? This is the 85 in this way, and this is 45 in the opposite. So somewhere here, it is 45. So please tell me how I will have the value here. 85 minus 45. Yeah, that's right. It is 40. Look what happened. Current, or this is the VR. This is in fact the equivalent, the voltage on the imaginary part. As you see, the E, it is in fact here. So everything is correct. Everything is correct. Right. So as you see, that looks like the AC analysis. In fact, for using the polar or rotular forms of the number, in fact, using the complex numbers. Okay. What we can do also here, we can find the power which is delivered to our electronic circuit. Yeah. So let's extend this example to finding the delivered power to our circuits. Okay. So maybe you remember from the lecture, the power which is delivered, in fact, it is given by the V, I, and the power factor, the cosine phi, where the cosine phi, it is the phase shift between the voltage and the current. As you remember, this is the V, I, cosine, and this is the phi for V minus phi for current. Yeah, this is the same, and this is called like the power factor. Yeah, FP. Okay, in our case, it is equal. What is the input voltage here? This is the E. Yeah, the current, input current, it is I. So let's find the power which is delivered here. So the V for us, it is the E. The current, it is also the current. Cosine. All right. What is the module, in fact, between the phases for the E and I? Okay, let's coming back and let's take a look for it. Here for the V, we've got the 30 degrees minus, for the current phase shift, it is 83.13. So this is the same like the E, I, cosine with the angle. This is the module, so it is the 53.13 degrees. Okay. So it is equal. What's the value? We have to put it here by E and I. It modules. Yeah. So the module here for E, it is 50 volts times the current. Current, it is 5 amperes. Okay, how much is the cosine from that angle? It is 0.6. So it is 450 times 0.6. It is 150 watts. That's the power which is delivered to our circuit. I don't know if you take a look at some very strange thing. Look, what is the input voltage here in our circuit? 50 volts. What is the voltage across the capacitor? 87. It is higher. It is higher than input voltage source. Okay. So as you see, for AC analysis, it is possible to get the higher voltage across the coil or capacitor. You have to remember. Okay. Okay. So, are you still there, or you just sleeping?
We're still here.
How you feeling?
Pretty good for now.
Okay, so let's make the last one. Okay.
All right.
Okay.
I've got a question also.
Yes.
Let's suppose that we have in this circuit two closed loops, and for example,
In which one? In which one?
In the third task.
Yes.
And let's suppose that between terminals we've got a wire which is closed loop. Can we use here Kirchhoff's voltage law, for example, to determine, for example, V1?
Which theorem? Because I don't hear you.
Kirchhoff's.
Kirchhoff's, yeah, of course.
Voltage. Okay.
Yes.
But here I suppose that we need to have rectangular form. I think.
Yes, because we using the Kirchhoff voltage law, yeah.
Yes.
We have to summing up some components. That's right.
Yes. Mm-hmm.
So as you see, we have to use the rectangular form. Yeah. In this case, if we wanted to, if we were able to use the VDR, yeah, we've got such a formula.
Multiplication.
Yeah, we got a multiplication. We have to divide it something. And this is much more easier to make it by the polar form. Yeah. However, if you choose, as you said, the Kirchhoff law, then you will have to operating on the rectangular form. That's why the way so another way to solve this example by the Kirchhoff voltage law, I think it will take much more time. Yeah.
Okay, but it's possible.
Yeah, I think yes. You know, the practice shows that it is true. It is true. Sometimes it is better to take a little time to finding finding make the conversion from the rectangular form to the polar one, if we will see that we'll have much more multiplication on dividing the numbers. So we have to just take a look at our expressions. Yeah, what types of maths no, functions we've got more multiplication, or for example, we have to adding something. Yeah. So that is the first choice to starting to solve the examples. Yeah, because I think it's better to make it by much more easy way. Yeah, and we reduce the points where we can make the mistakes. Yeah.
One question. This is 50 volts peak or RMS?
This is the this is the RMS, of course.
Okay.
This is the RMS. I will show it, in fact, in the next example. Yeah, how it looks like. Okay.
Okay, thank you.
Thank you. Okay, so let's doing the next example, and it looks like that. We've got some voltage source which is given by that values 4 volts with angle 0 degrees. We've got the R1 resistances, which is OK5 ohms. We've got some capacitor, which has the reactances equal 10 kilo ohms. Okay, some coil, and we've got some resistances R3. It is 3K. This is the XL 2K, and here we've got the V3 value. However, here we've got the extra R2 resistances, which is equal 1K, and here we've got the E1 voltage source equal 12 volts. Okay, what is the case in this example? We have to determine the sinusoidal expression for V3 voltage. However, we have to use the superposition theorem. Okay, so okay, superposition theorem we can use when we've got the at least two voltage source, of course, yeah, or current source. Anyway, sources. At least we have to have two sources. And we've got it. We've got the 1 and 2. How the superposition theorem works? In fact, it is very simple in general. We have to take the first voltage source, the another should be taken off. And for the only one source, we have to finding the V3 volts across the R3. Then we take it off the first one, we come back with the second source, and we calculating the voltage across the same R3 resistances for when the second voltage source is enabled. Then, according to the superposition theorem, the V3 voltage, it is equal the sum of the voltages when the first voltage source was present and the second one. Yeah. So, as you see, first of all, if you take a look at this example, please tell me what type of voltages we've got here.
AC and DC.
That's right. As you see, here we've got the DC voltage source, and here it is the sinusoidal one, AC. Yes. So we've got the different type of sources also. So in general, the V3, in fact, according to the superposition theorem, will be equal V3 for DC source plus V3 for AC source. Yeah. Okay, so let's do it. And now we have to separately calculating the V3 for DC, where DC source is enabled, and when the AC source will be enabled. Okay, great. So for DC, source we've got E2 should be removed, so it should be 0. So when the voltage source is 0, when it is short circuit. So our circuit will be looks like that. Okay. As you see, this is the DC sources. This is DC source. So if it is DC, so we have to replace the capacitor and the coil by what? Capacitor for DC analysis, it is what? It is open circuit, because we've got between the plates the electric material. So it is the open circuit here. The ideal coil for DC, it is like just the wire with the resistances equal 0. So the coil, it is represented by the short circuit. And here we've got just the R3, and we have to find the V3 value for DC, of course. All right, so how many it is? Look, what you can see here, the R3 and R1, it is connected together in parallel, as you see. That's right? That's right. So as you see, we've got a situation where we have the 12 volts, we've got the two resistances where the R prime, in fact, this is the parallel connection between the R3 and R1. And here we've got the V3. Yeah. Look, this V3 voltage, V3 prime, in fact, it will be the same like here, V3 DC. Why? Because these two resistances are connected in parallel, so the same voltage should also be across R1. Yeah. So, in fact, the V3 for DC analysis, it will be the same like V3 prime, and it is equal, okay, using the voltage divider, we can very quickly calculating it. Input voltage, it is 12 volts times, okay, here we have to put the R prime because we wanted to find the V3 over the R prime plus R2. So we have to find the R prime value. Yes. Okay. So the R prime, it will be equal R3 R1 plus R over the R3 plus R1, and this is the 50 ohms times 3K over 3.5K. So it is around 429 ohms. Okay. Okay. So let's coming back to our example, our V3 DC value. So it is 12 volts times 429 9 ohms over the R2. It is 1K. This is 1K. So it is 1K 429 kilos. Okay. So how many it is? It's around 3.6 volts. Okay. So we can say that we've got the voltage value V3 DC. It is equal 3.6 volts. Okay. Well, let's starting the AC analysis. For AC source, we'll have we're coming back with the E2 source. We've got the R1 here. We're coming back with the capacitor XC, with the coil XL, with the R3. What happened with the R1? Sorry, R2 resistances. Because we have to remove the E1, so the E1 voltage source should has the 0 voltage value. So we have to make the short circuit for the E1. So as you see, the R2 resistances will be short circuit to the ground. Why? Look, the same circuit can be drawn in that form. This is R2, and here yeah, and so on, yeah. Okay, so as you see, this is the same. This is the same. So if I have to make the short circuit here, as you see, the R2 resistor is connected to the ground, in fact. So that's why the R2 resistances, it is connected to the ground in that way. Okay, so now we have to find the V3, yeah, on these resistances. How we can make it? Look, I see here some group of impedances. This is the group of impedances. This is the group of impedances, and this is just the impedance of the resistances. Look, if I will find the Z1, Z2, and Z3, I will get the circuit which will be looks like that. And look, to finding the voltage across the R3, firstly, I will have to find the current which is passing through by these two components. So by the Z3 impedances. Okay. Sorry, I2, and this is IS, for example. Yeah. So how we can find the I3? We can use here the current divider rule. That's right? I think yes. But firstly, I will have to get the IS value, the input current value. Okay. So first of all, let's finding the Z1, Z2, and Z3. Z1, it is given by just the resistances, so it is the equal R1. So it is the 0.5 K with angle 0 degrees. Okay. What about the Z2? Z2, in fact, this is the parallel connection between the impedances of the resistor R2 and XC. R2 parallel with the XC. So it is equal R2 times XC over R2 plus XC. So do you see that everything, there's nothing is changed here to finding the parallel connection, series connection between the impedances? It is the same. Only we've got a different type of numbers. Here we have to operating on the complex numbers. Okay, so it is equal R2, it is 1 kilo ohm, yeah? So it is 1K with angle 0 degrees times XC. XC, it is 10 kilos. This is 10 kilos. This is 2K. This is 10 kilos, but this is the capacitor. So the angle is minus 90 degrees. Okay? Over, all right. Look, here we've got the sum of the two numbers. So the R2, it is pure resistance, is 1K, real part of the number. XC, it is minus JXC. So minus JXC, this is the capacitor. Okay, XC, it is equal 10 kilos. So it is, this number looks like that. Okay. Okay. So in nominator we'll have how many? 10K squared with angle 0 plus minus 90, so it is minus 90, over the 1K minus J 10K. However, we have to divide it to numbers. So first of all, here we have to convert it to the polar form. Okay, how many it is? It is square root of 1K plus 10K squared. How many it is? It is 10.05 K with angle. Angle, it is the Arcus tangent function from minus 10K over 1K. So it is the Arcus tangent from minus 10. How many it is? Minus 84.29 degrees. Look, the K is reduced with the power, of 2, and it is equal 10 k over 10.05. It is 995 around, with angle minus 90 minus minus, so plus 84.29. So it is minus 5.71 degrees. That's the Z2. Z3, it is the, as you see, R3, oh sorry, R3 plus XL. So it is 3K plus J, because this is the coil, 2 kilos. Great. So now it is very simple, and let's finding the polar form for this number. It is 3K squared root from 3K squared plus 2K squared. It is the 3.61K with angle arcus tangent from 2K over 3K. So arcus tangent from 2 over 3. So it is the 33.69 degrees. Okay, so we've got the Z3. Great. So we've got the Z1, Z2, and Z3. Now, we have to find also the current IS, yeah, the input current IS, which is needed to finding the current I3 using the current divider rule. So how we can find the current IS? First of all, we have to find the total impedance, which is observed by the voltage source. Yeah? So what is the total impedance in this case? It is the parallel connection between Z2 and the Z3 plus Z1, because Z1 is in series. Okay. So the Z total will be equal Z1 plus the parallel between Z2 and Z3. So it is equal Z1, it is 0.5K, that's all, plus Z2 times Z3 over Z2 plus Z3. Okay. So it is equal 0.5K plus. All right, so because we've got the multiplication here, so let's use the polar forms of this number. Z2 okay, Z2 it is here. So it is 995 with angle minus 5.71 times Z3, it is here 3.61K with angle 33.69 degrees. All right, over the sum of these two numbers. Whoa. Whoa. Okay, Z2 is given by the polar form, which looks like that. So now we because we have to summing up two complex numbers, so this number we have to convert it to the rectangular form. Yeah. How many it is? I make it, and it is 990 minus J 99. So I will have 990 minus J99 plus Z3. Z3, it is polar rectangular form, it is here. 3K plus J2K. So this is equal. Okay, so let's multiply these two numbers. So it is equal 3.592 mega ohms with angle minus 5.71 plus 33.69. So it is the 27.98 over the. Okay, we have to summing up two complex numbers in the rectangular form. So it is so easy because we have to just summing up the real and imaginary part separately. So it is the 3.99k, okay, minus J99 plus 2k. Whoa, it is the plus J 1.901. Okay. Okay. So this number should be converted to the polar form because we have to divide it to numbers here. Okay. How many it is for this number? What is the representation of this number in the polar form? So again, this value we have to power it plus this one is powered by 2 and square root of it. It gave us the 4.42k with angle, and the same story like here. However, here we have to put the 1.901k over 3.99k. So it gave us the 25.38 degrees. So everything, this is the plus. So it is equal 0.5k plus, and here we have this number over this one gave us the 812 with angle. This angle minus this one gave us 2.5 degrees. So we've got the ZT, Z total, and we have to summing up two numbers. However, one is representing the rectangular form, the second is in the polar form. So as you see, again, we have to replace the polar form to the rectangular one because only that is possible. This is one possible way to adding to complex number in the rectangular form, of course. So it will be equal 0.5k plus, and this number, if I will calculating its rectangular form, it is 811.2 plus J 35.42. So it is equal. I have to just summing up the real part of the numbers here. So it is the 1.3112k plus J 35.42. This is our Z total value. Because somewhere we have to divide this number. So let's calculating in this moment it's polar form. The polar form here will be equal 0.312k with angle 1.53 degrees. So it is the same in two forms. Okay, so now the current IS, it is just the E, over the total impedance. Yeah. So it is equal. E, it is 4 with angle 0 degrees over ZT. ZT, because we have to put it here in the polar form because we have to divide it to numbers. So it is equal 3 over 1.3 kilos. It gave us 3.05 milliamps with angle 0 minus 1.55. It is minus 1.55 degrees. So that's the ES. Great. So now, if you're coming back to this, finding I3 current, let's implement the current divider rule. So the I3 will be equal the input current IS times. Here we have to put the resistances where, or impedance here, where we not observe the current I3, which is passing through by. Where we have to put it here, the impedance where this current is not passing through by it. So we have to put the Z2 over the sum of the impedances of the current divider rule. So Z2 plus Z3. Okay, so it is equal. The current, it is 3.05 milliamps with angle minus 1.55 degrees times Z2. Z2, it was here. It is 995 with angle minus 5.71 degrees. Okay. Over the Z2 plus Z3. Okay, so again, because we have to summing up two numbers, so we have to put it here, the representation in the rectangular form again. So it is okay. We know how many it is because we calculate them previously. Okay. In fact, we're calculating it here. Okay. So this is equal. So it is equal. Let's multiply it to these numbers here. So in nominator we have the 3.035, yes, with angle minus 1 plus minus 5.71. It is minus 7.26 degrees over. Okay, we have this number. We have to represent it in the polar form. We know it, how many it is, because we've got it here. Yeah, this number, this is it in polar form. So it is 4.42K with angle 25.12. Okay, and this is equal. If we divided these two numbers, we'll have the 0.686 milliamps with angle minus 7.26 minus 25.48. So it is the minus 32.74 degrees. That's the current I3. Okay, we've got the currents. Let's coming back here. We've got the current I3, which is passing through by Z3. However, this I3, in fact, is passing through by the series connection of the two impedances. So, in fact, this current I3, it is the same current which is passing through by XL and the R3. So V3 for AC, it is in fact the voltage drop on these R3 resistances due to the current, I3 current passing through it. Okay. So the voltage V3 for AC analysis, it is given by the current I3 times R3 according to the Ohm law. So it is equal 0.686 milliamps with angle minus 32.74 degrees times Z3. Z3, it is the 3 kilo ohms. Yeah, this is the multiplication. So let's represent the impedance here. Sorry, I have to put it here, the Z3. Sorry, Z3. Z3, it is the just the R3 because this is the pure resistor. Okay, so the impedance of the Z3, it is represented in the polar form, like the 3K with angle 0 degrees, because we've got the multiplication here. That's why I wanted to put it here, the polar form. Okay, so it is equal 3K times 0.686 milli. It gave us the 2.06 volts in this case, with angle minus the same angle, because it's minus 32 minus 0, oh sorry, minus 32 plus 0, it is the same angle. Okay, so as you see, we've got the V3 value. So let's coming back to the beginning of the examples, and according to the superposition theorem, V3, it is given by V3 produced by the AC source only, plus V3 which is produced by the AC source only. So it is equal 3.6 volts, it is for the DC, plus 2.06 volts with angle minus 32.74 degrees. Okay, however, in this case, we have to determine the sinusoidal expression for V3 voltage. Okay, so we have to change this number, this voltage, which is represented by the polar form of the complex number. We have to represent it by the sinusoidal function. Great. What is this value here? This is the RMS value. As I remember, the Jakub had some question about it. Yeah, what the values here? This is the RMS. Anytime in the polar form, this is the RMS value. Okay, what is it? This is the phase shift. Yeah, that's right. The angle phi. Okay, what is the mathematical expression for the sine waveform in general? This is the, for the V, it is the V max times sine omega t plus minus phi. Okay, so in our case, if we've got such a number, we've got the VRMS value, it is given, it is 2.06 volts. So because here we have to have the maximum value, yeah, so how we can find the maximum value here? On the lecture, I told you what is the relationship between the VM and the VRMS. And only for the sine expressions, there was the magic number, square root of 2. Yeah. So you have to remember that Vmax it is equal square root of 2 times VRMS. Yeah, that's right. Or VRMS, it is the same like Vmax over square root of 2. But only for the sine waveforms. Only for that. Okay, so let's find the VM. VM, it is equal square root of 2 from VRMS. So it is given, and so it is equal square root of 2 times 2.06 volts. So it is equal 2.91 volts. And this is our Vmax. Okay. What about the phi? The angle phi is here. So we've got it here. This is minus 32.74 degrees. So finally, the V3 expression is given by DC value 3.6 volts. So we can say that the sine waveform, which is here, is just shifted by the DC value. It is shifted by 3.6 volts up. Plus, and now the V3 for AC, yeah, we have to replace by the sine expression, where here we've got the maximum value, which is equal to 2.91 volts, sine omega t minus 32.74 degrees. So that's the end of this example. That's the mathematical expression for V3 using the superposition theorem. We can make this example in fact only using the superposition theorem. Because we've got the two different types of sources, DC and AC. All right, so as you see, it take us the much more time at this moment. However, it was the first examples which based on the complex numbers. That's why I wanted to show you just step by step, very, very slowly, what we have to do to solve such examples for AC analysis. And also, we used here the another theorem, like the superposition theorem, VDR, C either rules. Okay, guys. So that's I think that's enough for today classes. So I suppose that everything is clear. Yeah. So you know how you can solve the examples based on the complex numbers. So what else? Please make it. Please make the examples for the AC analysis according to this the books what was given at the beginning of the course. So please, Grzegorz. Grzegorz is present.
Yes, I am.
So Grzegorz, you send me the some examples what was solved by you. I can say that excellent work.
Okay, thanks. I started with calculating the impedance and stuff like that, but then I realized that previous topic wasn't about impedance, but about the inductors and capacitors, so I went back to this topic.
Okay.
So I also have some task with impedance and stuff like that, but rather simpler task than we have made today.
Okay. What else?
So I have one question.
Yeah, Tomasz?
About the lecture on Thursday.
Yeah.
When will it end? Because we have programming classes and they may collide.
So could you repeat?
How long is it going to be? Because we have programming classes at 1 p.m. and I think they could collide.
Okay. So at the first at the 1 p.m.
Yes.
Yes.
Okay, at the 1 p.m. Okay, so we have to finish it before it.
Okay.
So we'll start on the
9:15.
quarter past 9, yeah, p.m. That's right.
Yes, please.
Yeah. So and we, I can tell you that we'll finish it before the first the first p.m.
Thank you
You're welcome.
very much.
Okay. So I'm planning to show you on the lecture. I'm planning to show you how it looks like the frequency characteristic of the resistor of the coil, and maybe I will find some so capacitor, and maybe I will find some coil in my home using this analog discovery 2 unit, and I will show you in real how this plot looks like. Yeah. Because the last time I will talk about the impedance, how it looks like the impedance of the real resistor, capacitor, the coil, yeah. And I told you that for the higher frequency, in fact, the capacitor, sometimes it is not the capacitor, but it looks like the coil, yeah. Or change its character, and also the capacitor are changed the character to the inductor one. Also the resistor, the real resistor, it is not just the resistances, but I will show you plotting in real time the characteristic frequency characteristic that in fact the resistor, in fact it is not the pure one. The capacitance is present there for the higher frequency. This discovery the analog discovery board here is limited to the 10 megahertz of frequency. So only in this range of frequency to the 10 megahertz I will be able to show you, but it is enough. Yeah, I will take the higher resistances and then you will see what happens in fact when the frequency is going up. Okay.
I have the question.
Yes, Grzegorz.
Is the analog discovery some kind of vector network analyzer, or it works on a different basis?
This is the network analyzer. That's right, and it working in that way because this setup has the internal generator. Yeah, and this generator is. This generator is plugging to, for example, to the resistances. Here we have to have some load resistances. And how it works? This generator is swept in frequency, so we are starting from, for example, 1 hertz to the 10 megahertz. And at the same moment, of course, this board has also the scope with 2 inputs, 2 channels. One of them is connected to the input, yeah, and the second channel is connected to the output. In such way, we can find the frequency characteristic of this element because here we have the transmittance. In fact, we'll observe the transmittance of this element, which is given by that formula. Okay, the transmittance, it is given by formula U out over U in. Yeah. So for any frequency, any step of frequency, this board or the analog discovery board take the output signal divided by the input signal, and for any frequencies they will plotted the transmittance, and which is looks like, for example, dots for the real resistor. Yeah. However, here we've got 10 megahertz. This is the 1 megahertz here. Also, in such way, we can find in fact, this is the frequency characteristic of this resistor. Also, it is possible to find, for example, the frequency bandwidth of the amplifier. Yeah. If you have some amplifier, minus entities, minus and pluses here. For example, something like that. We've got such the circuit, and we plug in the generator with the sweep, and we put it here, the first channel of the scope, and here we plug in the second channel. Also, this board will generating the frequency characteristic of this amplifier also. Yeah. So that's the in fact the general information about how this the electronic circuit, this analog board are creating or finding the frequency characteristic, or how the vector analyzer is work. Okay, Grzegorz?
Yes. Okay. I was just curious about the local generator of this analyzer, because nowadays there are Chinese vector network analyzers that go up to 900 megahertz. So that's very interesting.
Yeah. How many? 900?
900 megahertz, but I think that now it's open source and somebody changed the code to 1 point something gigahertz. And
okay.
I've ordered one to tune the antennas and bandpass filters
Okay.
for RF.
Okay. What was the cost of it?
About $40 on something like that, so 150 zł, jakoś tak.
Wow. What's the name of the company of it? What's the name?
There are many, but if you type nano VNA, or I think it was micro VNA, there are two types. One is 2.5 inch display, and one is 4.3 display. But I will check. I think it's nano VNA or something like that.
But okay, but this is just the vector analyzer only.
This is vector analyzer with
generator.
Measure SWR, Smith chart. I don't know if it's very precise for Smith chart, but presumably it works.
Yeah, this analog board here, of course, this is much more expensive, because for the staff, university staff, it is around 800 zloty, and around the 1,000 zloty it is for the people, for example, which is not connected with the universities. However, this analog boards has different, for example, units like the DC voltage source. You can also plug in the different type of interfaces, like the I2C, SPI, UART.
Yes.
Yeah.
So it's also a logic.
Yeah, that's right. You've got the scope here also, which is working to, I think, 100 megahertz. Yeah, it works to the 100 megahertz of the scope. You've got the 2 channels, and this is the 14 bits of ADC converters here. So it is nice. It is nice because you are buying it. So you've got the 2 channels of dual channel scope. You've got the generator to the 10 megahertz. You've got the vector analyzer, spectrum analyzer also, because you can see how it looks like the FFT of your signal. Also, you can calculating the noise flow, signal to noise ratio, something like that. There's many. You've got the pattern generator also. It is not only the sine waveform. Yeah. So, however, the cost is higher, of course, in this case. But this is analog. Yeah, that's why. This is like
it's still impressive.
Yeah, this is like the like with the cars. Yeah, so if you wanted to buy the, I don't know, the Volkswagen or something like that, you have to pay for the for that, because it is just a Volkswagen. Yeah.
And the fact is there is no BNC connectors isn't limiting here.
No, Jakub, you have buy the extra extended board where you have the BNC connectors there. Also,
because I feel like if I would start to just plug in the small cables, it would introduce some noise.
Yeah, of course. Yeah. However, there's a few modules which is plug into the discovery module also, and you'll be able to, for example, plug in the board where you have the BNC cable, and that way you can reduce some noises for when you operating for the higher frequencies. Yeah, especially if
I see
you
it
really,
like add-on, and it's cost 2,000.
Yeah, that's right. Really?
Bundle with everything.
Whoa, I don't think so. You can take a look at the Kamami shop.
I've put a link on the chat.
Oh, okay. I bought it by the around 800 zloty. Maybe price will go
But
up.
with the extensions or just the
Just the analog board.
because it's 2,000
extended,
for the analog discovery and all the extensions.
but all of them.
Most, I guess.
Probes, PNC connectors.
No, yes. What's the cost of it? The basic connector extension board.
So bundle with analog discovery and everything else is 2,000.
Okay. Whoa.
So probes, these BNC connectors.
Also the probes. Mm-hmm. Okay. No. Sometimes there's no any way. If you wanted to make something at home, especially, I can tell you that I bought my private scope, which is working to the 200 of megahertz. I bought it from the. This is what the company is. It is Owen, I think. This is Chinese company which produced the scope, the Owen. and I take the hammock oscilloscope from the job what we have in our our laboratory, and the same signals at the same moment I'm plugging to the Owens and to the hammock's oscilloscope, and believe me, I saw that everything was the same. The quality of the signal looks like the same. However, the Owen cost was around 3,000 zloty, and the hammock cost was under 10,000 zloty. So as you see, that's the difference. All right. Okay, guys. So we'll see on Thursday on the lecture. Yeah, that's right.
Yes.
Yeah.
All right. So thank you for